Hey, all right, students, let me run through the solutions. This would be a good time for you to kind of check your work. You can do two things here. You can kind of self-grade and see how you do and get an idea of your grade before I get a chance to grade all them, because it'll take me a little while. And of course, the other thing is to look for your mistakes and learn from those mistakes. And when you realize what you did wrong and then hopefully see what was the right way, uh, you'll learn from those mistakes here. So let me start with the first problem here. Maybe I'll put the second page of the exam off to the side here. But in this first one, it says that we have a graduated cylinder, so kind of this looking thing, and it's filled with 100 cubic centimeters of turpentine at 25 degrees Celsius. And then a 250 degrees Celsius, and here's its volume. And this is its volume when it's at the high temperatures, of aluminum block is then placed into the turpentine, and then the density of each is given here. Okay. Assuming that the graduated cylinder is fully insulated. Okay, so this hopefully looks a little bit like the lab we did, as well as the number of homework problems where the heat energy from one goes to the other. And so using the first law of thermodynamics, the conservation of energy, we can, see what this final temperature is. I think that's where this is going. Yeah, because again, the turpentine is going to warm up and the aluminum is going to cool down. They give the specific heats. And then, okay, what is the equilibrium temperature? And so starting here with A, I guess we would say, all right, the Q1 plus Q2 has to be 0. So one's going to lose energy, one's going to gain energy. They're going to be equal because of the first law of thermodynamics. So we have the MC delta T and the MC delta T of the other stuff. Maybe I'll call the first one here the aluminum and the second one here the turpentine. Okay. And of course, part of this is the mass. So maybe we better say mass is density times volume. And we're going to need then the mass of the aluminum as well as the mass, and I'll just put a little T for turpentine. All right, so with that involved here, let me start with the aluminum. Let's see, they say the density is 2.7, and they say its volume is 50. So we're working with 135 grams of aluminum. Oh, and I guess I don't need a calculator for this one because it's an even 100 multiplied by 0.84. So that's going to be 84 grams of turpentine. Okay, so continuing on here, the aluminum is 137 grams. The specific heat of the aluminum was given right here as 0.9. And the change in temperature would be the final minus what it started at, which was 250. So the aluminum is the hot piece that you are putting in. And so we put that in. Let's see. And that should be, a negative number. So the energy is going to come out of the aluminum. And the same amount that goes out of the aluminum goes into the turpentine. And so I'll take the 84 grams. The specific heat is 1.72, just to confirm that. There we go. And then we have a final temperature minus the initial, which was 25. And now solve the math here. This first one would be 135 times 0.9, and I'll write that as 121.5, final temperature minus 250. This one here, 84 times 1.72, that is 144.5, final temperature minus initial. I guess we could distribute it. We have some big numbers. So just to keep my numbers a little bit small, let me just divide everything first by 121.5 so that this number doesn't get so big, and then also this one, which is this number then divided by that number. All right. And so we're looking at, looks like about 119. Maybe I'll just do a 1.189. Okay. And then this is final temperature minus 25. Still equals 0. You see, that way when I do the distributive property, I'll have that as a 1 added to this. And so we're looking at 2.189 final temperature. And then this one here would be that number times the 25 when I do the distributive property. That's a negative. And so if I put it together with this negative, 250, and move it to the other side, it's now going to be a positive 279.7. And that should give me then to my final temperature when I divide by 2.1, was it 189? Yeah. And then this is my final temperature. So we're looking at about 127.8 degrees Celsius for the equilibrium temperature if it is completely insulated. Okay, nice. Now, the next part of this question, second half, B, it says, what is now the total volume of the reading here? And if we didn't have any thermal expansion or contraction, because it looks like the turpentine is going to warm up, so it's going to get bigger, and the aluminum is going to cool down, so it's going to get smaller. We would just, of course, the total volume would be then the 100 plus the 150, and we would look on the side of the graduated cylinder and read 150. Actually, this one doesn't go up to 150, so hopefully that's... we would be doing this in a bigger graduated cylinder, hopefully, if those are milliliters, but they usually are. But ignoring the limit of this graduated cylinder, we would expect kind of something like this, that, it's 150, but the turpentine warms up, so it goes more than 150. Now, the aluminum cools down, but as we'll see here, the change in aluminum compared to turpentine is pretty small. And so we're going to end up with something bigger than 150. In fact, turpentine changes by quite a bit. That's why I use it a lot for thermal expansion, so we have a number that really can change. And so it wouldn't surprise me if we're like 155, 160, and there'll be quite a bit more here, surprisingly more than you would have thought when you just put 100 and 50 together, and you're thinking, oh, that's going to be near 150, but it's not. It's going to be measurably bigger than that. But let's give it a try. And so I'll start here with the change in volume, and maybe I'll go the turpentine. And maybe below it here, I'll go change in volume of the aluminum. Because as we did these expansions, we said for a liquid, you would have the beta, the initial volume, and the delta T. But for things that are solid, the linear expansion has to be turned into a volume expansion by multiplying by 3. And then you'll have the original volume times delta T. So in the case of the turpentine, if we look at here, what is the total volume of the turpentine aluminum system when equilibrium is reached? And they got the linear coefficient of the aluminum. So that would go here. So that would be 3, and then times the 24 times 10 to the minus 6. The initial volume is 50. And the change in temperature is the 127.8 final minus its initial, which is 250. And so that's why that's a negative number. And of course, the aluminum is cooling down, and the aluminum is going to get smaller. And in fact, before I go back to the turpentine, why don't I just do the aluminum here? So 3 times 24 times 10 to the negative 6 times 50 times 127.8 minus 250. And we're looking at a minus number, good, 0.440 cubic centimeter. So half a milliliter, half a cubic centimeter, it contracts. But like I said, I'm quite sure the turpentine is going to get more than that because you can see that in the number with the beta factor. The volume expansion is this 9 times 10 to the minus 4, which hopefully, and luckily here, we don't have to look any of these numbers up. There's quite a few numbers we need, and they're all given in the problem. But 9 times 10 to the minus 4, the initial volume is 100. The change in temperature for the turpentine is its final temperature minus its initial. And let's get a number here, 9 times 10 to the negative 4 times 100 times 127.8 minus 25. And yeah, see, look at that. That's going to grow. So plus 9.252. And so sure enough, the turpentine grows more than the aluminum contracts. So if we're after the total volume, we'll take the initial volume of the turpentine plus how much it expands. We'll also take the initial volume of the aluminum plus how much it contracted, so plus a negative number. And so, well, actually, put those three together, I guess, in my head. That's 159.252, and then subtract off 0.440. And so it looks like we're looking at 158.8, pretty close to 159 milliliters or cubic centimeters. And that's, like I said, I think a little surprising because, you know, you look at the graduated cylinder and, you know, you're like, okay, and this one, like I said, it's a little small, but you already got 100 in here. Then you're going to add 50 more, so it's going to go up to here. But because things warm up, it goes up a whole nother 10, which on this graduated cylinder is about that much further. And you'd be like, whoa, where'd that extra fluid come from? So, all right, well, hopefully that is helpful. Hopefully you got all that completely right on the first go around. Let's look here at number 2. And number 2, as you will see, is really the homework with a little twist. So hopefully you did the homework and studied a couple times. And if so, I think this will go really fast for you. If not, you might take a little longer than you anticipated on this one because you're going to have to think this one through. But I guess that's kind of an award for really thinking about these homework problems more than once and really doing them deeper, especially part B where we've got some calculus to do. This one, the numbers make it real simple and kind of quick. I mean, watch this. You might remember this one. It says, like the homework problem number 39 in chapter 20, you have a bar of gold and it is in thermal contact with another bar of silver. And they have the same cross-sectional area. It kind of looks that way in the picture. But unlike 39, the gold bar and the silver bar have different lengths. So in the homework problem, they had the same length and you were asked to find the temperature at the joint between them. Here, they're going to have different lengths. But as you continue on reading, it says here, one end of this compound bar is maintained at 80 and the opposite is maintained at 30. And so the temperature halfway between them is 55. And so they're going to say that you adjust the lengths here until the joint between them is halfway. It's half the difference. And then it says, if the whole length of this is 1 meter, how long is the gold bar? And so the idea here is when we reach this steady state, it means the temperature gradient drops from 80 to 30, but part of that has to do with the conductivity of the material. And we learned that silver has a stronger conductivity than gold. And so what we're going to say here is we have the flow of energy, which is minus Ka times the temperature gradient. And what makes this problem, in both parts A and B, is let's just call this P for the power, the flow down here. Because when we get in steady state, what we're going to say here is every bit of energy that flows in flows all the way down and out. So that's why the temperature doesn't change. Everything that flows in equals what flows out. Obviously, if more energy flows in than out, there'd be an increase in temperature, or the other way around, there'd be a decrease in temperature. So that's something to think about, and hopefully something you don't have to really think about during the exam, because you already hopefully gave this some deeper thought while you were doing the problem. So what you could do is then say the power flow from the gold piece and the power flow from the silver are the same. And so when you set it up that way, and I'll just do absolute value, so I'll ignore the minus sign here, but you're saying the flow, the conductivity of the gold, cross-sectional area of the gold, the change in temperature of the gold, and the length of the gold would be the same as the conductivity of the silver, the cross-sectional area of the silver, the change in temperature of the silver, and the length of the silver. And like the homework problem, the areas are the same, so they can drop away. You don't really need to know what those are. Now, not like the homework, but in this case, the delta T's are also the same. We've set it up so that this temperature difference is 25 through the gold and also 25 through the silver. And so this would say that the conductivity of the gold over the length of the gold must be the same as the conductivity of the silver over the length of the silver. And the conductivity is, again, what you probably did in this problem. Let me grab the textbook. But hopefully during the exam, you either grabbed your textbook, or maybe even grabbed your homework to say, hey, let's take a look at these numbers that I used. I suppose you could even look at the solutions for it if you did not do it during the you didn't have it with you. But the conductivities were done in chapter 20, as the problem says, and I think it's table 3, so it's a little bit further down in the chapter. I must have passed it. Oh, here it is. It's over on the side here. Yeah, table 3. And let's see, for silver, we got, let me just put that right over here, 427. And for gold, we have 314. Okay, so as I put in the numbers for the which one do I want here? Oh, gold must be the 314. Let me just write the equation. 314 over the length of the gold must be equal then to the 427 over the length of the silver. Or if you want, you can rearrange this by putting the length of the silver over here. You can put the length of the gold over here. And then you would have the 427 divided by 314 and 1.360. Yeah. And so kind of makes sense that the silver piece is going to be a little bit longer than the gold piece. Actually, more than a little bit here. It looks like we're looking at maybe, 36% longer. And it makes sense because the conductivity of the silver is so much better. So to give them at the same rate, you're going to have a shorter piece of gold to conduct at the same rate as the longer piece of silver, because silver has a physical property of transferring energy better. Now, also keep in mind that the length of the gold plus the length of the silver is 1 meter. So if we take the length of the gold and right here do a little substitution for 1.360, length of the gold equals 1. This comes out to be 2.36, length of gold equals 1, or ultimately length of gold is 1 divided by 2.36. And so we're looking here at about a 0.42, what was it? 424 meters. I don't think it asked, but I might as well do the silver. Let me subtract 1 meter and get 0.576 meters for the length of the silver. But I'll just circle this one because the question here just says, if the whole length is 1 meter, how long is the gold bar? Okay, so that's all we need to find is the length of the gold bar for part A. Now, part B, as the problem says, this is like problem number 62, also from chapter 20. But now we have a hollow sphere. And if you remember this one for the homework, it was a hollow cylinder. And it was kind of like a water heater or a hot water pipe where you could calculate the rate at which energy transfers in or, well, out if it was a hot water pipe. I guess if it was a cold water pipe, like one of these chilling pipes you see in a lab or maybe some industrial area. But anyways, energy would be flowing in and warming up the water. We don't have a pipe. This is just a sphere of some kind. And so some kind of container. Okay. The inside is maintained at 0 degrees. So somehow the inside is at 0, probably some like ice bath or something, while the outside is at 100 degrees. So, you got it maybe sitting in boiling water. So we got ice water inside, we got boiling water on the outside. The walls of the sphere has a thermal conductivity, and they don't say what the material is. Probably better that way. They just give you a number. But that 79, that 80, that's usually about the level of like stone, concrete, that kind of thing. But they give us the 2 radii. And then, of course, the same idea. When the energy transfer reaches steady state, what is the rate of energy conductivity? So starting with that same equation, dq over dt minus ka dt. And in this case, I'm going to put dr because instead of the energy flowing along a x-axis, it's going to be flowing in kind of a radial direction. And in this case, it would be flowing, inward. We got the hot on the outside. And so we should have a flow in the negative r direction. So it should be a negative gradient here, flowing inward. Okay. Let's see. So solving this, and again, hopefully you gave this a lot of more detailed thought while you did the homework. The attack on this problem is to realize that if you were to chop this thing into microscopic spheres, like we did back in A, we could argue then, we'll just call this P for power, that the flow rate has to be the same for every layer, every microscopic shell. Now, in this case, each shell is made out of the same material, whereas in part A, they were different materials. But unlike part A, where they had the same cross-sectional area, each shell would have a different area. You can, this is a sphere encased around a sphere, encased around another spheres, like maybe layers of aluminum foil. If you had like a baseball here, maybe I'll kind of give you a mental picture. Let me grab a baseball here and grab paper. Paper. Oh, maybe I'll grab the paper from the solution I just did here. But if you kind of wrap this, around it, and then you put a second one and a third one. I don't want to damage the paper too much here. But this is what I'm thinking in my mind, this stack of shells on my baseball. Oh, hey, what a great baseball here. All right. Oh, yeah, I remember this year. way back. Let me put this back on its stand here. All right. But here, as I have all these shells, it's, like I said, almost like A, but A had different materials, same cross-sectional area. This one, they all have the same A, but they have different cross-sectional areas. But the real key to our first step is to say they're all going to have the same power flowing through them. So I'll just put P for power. And then as I take the next step down, I'll say that the area that the energy has to flow through, and so these shells, this is the area of a spherical shell. And so now my equation has, two derivatives in it, or two differentials, one in terms of temperature and one in terms of R. And these differentials have been replaced with a constant value, and that's the key to the problem, because now I only have two variables. And like any calculus problem that only has two variables, try to separate them, put everything with R on one side. So in this case, I'll move the dr over to here and the r squared over. And the other variable, which is all the temperatures, and there's just a dt to the other side. Then you have the constants. It doesn't really matter where you put those. And so I'll just put them all together. I like that best. And in this case, I'll just put it on the left-hand side. But I've got this minus k, 4 pi, and power. And so now I can integrate both sides. And so in this case, we're going to go from 0.01 to 0.02. So we'll go from the inner radius to the outer radius. It's given somewhere in here, r, little r, and big R. And then the temperature is going to go from 0 to 100. We're going to go from the inner piece on out. And now the numbers are actually pretty easy. This is just a minus k 4 pi over p, and then the integral of dt is just going to be a t, so it's 100 minus 0. This one might be a little bit harder. You might want to think about it as r to the negative 2 dr, because when you integrate that, you add 1 to the exponent, so that's r to the negative 1, and then you divide by that new exponent, which maybe is best written as 1 over r with the negative in the numerator. And so this would be negative 1 over 0.02 minus a negative 1 over 0.01, which the two negatives can cancel out there. And grabbing my calculator to do this, I might go, 0.01 reciprocal, that's a positive one, and then minus, I'll just do this in reverse order, 0.02 reciprocal, and that comes out to be 50. So if I bring the p to the other side and bring this 50 underneath the 100, that becomes a 2, that becomes a 4 pi, and then the k was the 79, what was it here, 79.5. And so this will be the flow of energy. So 79.5 times, I'm just going to put that in 8 times a pi, and we're looking at 1,998. I suppose that's really 2,000 if we just do 3 significant figures. And so, and watts, this is the flow of energy that would be flowing in to this. And if it was, say it was filled with ice, I suppose we could take another step and ask then, okay, then at what rate is the ice in here melting in order for this to continue to happen? And of course, at some point, all the ice will melt. But there's number 2. Okay, on to number 3 here. Where did I put the second page? Right here. All right. So number 3 tells us that we have 2 moles of a, notice, diatomic gas at 300 Kelvin. And as it expanded from its starting point A, and so looking at the PV diagram here, A to 0.08, which is point B. Which, looking ahead, it looks like we want to fill in this table. So I'm going to put 0.080 right there already. So I know the volume. Which actually, working backwards also, they said this is at 300. Okay, so 2 moles of diatomic gas at 300 Kelvin is then expanded from its starting volume, so they don't say what it is, to 0.08, so point B, following this mathematical equation. Okay. Where pressure is measured in pascals and volume in cubic meters. Okay. The gas is then expanded adiabatically, so that's why you have this curve for the adiabatic looking here. The gas is then expanded adiabatically to its initial pressure. All right, so whatever the pressure is at A will also be the pressure at B, which, again, I don't quite know yet, but at least I'll just kind of chain those together. Finally, the gas is then cooled at this constant pressure back to its original state. What is the pressure, the volume, temperature of point A, B, and C? Oh, and then they give us a nice little hint. See, because if we start off with this at point A, we only have the temperature. We've got 2 unknowns. So we need another piece of information, and fortunately, we've got that. And so that's a perfect recipe. 2 equations, 2 unknowns. And so let me start there. And following the hint then, for number 3, I would say, all right, so PV equals to nRT, but pressure also equals 446,000 V to the 1/2 power. So working from that, I can replace the pressure here in this equation with 446,000 V to the 1/2. And when I multiply by that V, I add exponents. So that's 3/2. And then I get the N in this problem, which they said it was 2 moles. And R is 8.31. And they said the temperature is 300. So that's how I would put the 2 equations together to have just one unknown. So grabbing my calculator, 2 times 8.31 times 300. Divide that by 446,123,000. That would be v to the 3/2 power. So if I raise it to a 2/2 power, I should just get v by itself. And so that'll be a 0.050. So right here, I could go 0.050. Now, that actually gives me two ways to get then the pressure, because I could use then back at this equation or this equation. And maybe I'll just do this equation. And solving this for pressure, I'll just go 2 times 8.31 times 300. I didn't mean to hit enter, but I think I'm good. Then I can divide it by the volume, which would be this number right there. Okay. And so doing all of that gives me a pressure of 99,726. So just under 1 Pascal. Now, I was tempted to use this equation because we know it's volume, but it would also set us up perfect for B, because notice A and B are connected by this mathematical equation, which means that if you know either volume or pressure along either A or B, you can get the other one. And that's what I'm going to do to take advantage here of B, is I'm going to put it into this connection here and say, okay, so then the pressure would just be the 446,000 times the volume, 0.08, raised to a power of 1/2, which I'm going to write 2 to the -1 power. And I get 126,147 for the pressure. I guess it rounds to 8, but those are actually extra significant figures. I shouldn't go probably more than 3. But that is then the pressure. And then again, once you know 2 of these, you can always get the third from PV equals nRT. So to get the temperature at B, I'm just going to take the pressure, which I guess I already have in my calculator, multiply by the volume, divide by the N, number of moles, and divide by the R, 8.31, and that should give me my temperature. And so it looks like the temperature is 607 here. So that gives me all the things at A and B. As we mentioned earlier, once we know the pressure at A, we also know it at C. So jumping down here to C, we've got that pressure. And that actually sets us up beautifully, because B and C are connected, B and C, by the adiabatic process. So that means the pressure at B times the volume at B raised to a power of gamma would be the pressure at C times the volume at C raised to a power of gamma. And so B has the 126,148 and a volume of 0.08 and a gamma of, and this is where the diatomic has to come in here. Remember, gamma is CP over CV, and CV is the number of degrees of freedom. And so we have 5/2 R, 5 degrees of freedom for a diatomic. And if you add an R to it, you get 7/2. That reduces to 7 over 5, which is 1.4. So this is 1.4. Now, the pressure at C, we just reminded ourselves that it's the same as A. And then we have the volume at C raised to a factor of 1.4. And so I'll just do everything except for the exponent on the volume at C. And so I'd get 126, 148 times 0.08 raised to a power of 1.4. Then I can divide it by 99,726. And maybe wasting a little bit of precious time during a test, but I'll kind of write down that intermediate step. Don't want to do too many steps during an exam and make a calculator mistake. And that's just kind of my normal go-to. I like to just do everything except for the exponent, because then the last step is to then raise that to a power that's the reciprocal of that, so that they cancel off and you get volume to a power of 1. And so raising it to 1.4 reciprocal gives me a volume of 0.0946. So 0.0946. Nice. And I guess the final step is to again use PV equals to nRT to get the temperature like we did back in B. So I have the volume already in my calculator. Let me multiply it by the pressure, the 99,726. So there's PV. Divide by N and also divide by R should give me a temperature. Oh, good. A little bit lower because we know that the adiabatic expansion is a cooling process. It's doing work on the environment. So it dropped down from 607 to 568. And great. I think that completes number 3. Okay. Moving on. Oh, I'm out of paper on that yellow pad. Let me grab another yellow pad here. Okay. And go on to number 4. It's also page 4. So far they've all fit on one page. Here it says, and again, we got this part A and part B. It says a 2.5 moles of, and now notice, helium, so diatomic or monatomic gas, as opposed to last time was nitrogen, diatomic, neon, starts at 1 atmosphere, which I'm going to just remind myself is 101,300 pascals, because I have a feeling there's going to be questions about energy. Yeah, there's work, there's entropy, but those need to be in joules, so I need pascals. All right, of pressure and a volume of, and then notice it gave me in liters, but I'm going to change that to cubic meters, 0.055 cubic meters. Its pressure is held constant, and it is heated until its volume is doubled. Then it is heated at constant volume until its pressure is doubled. Okay, so if I'm doing a PV diagram, and maybe I'm starting right here, and I'll just put 1 atmosphere for pressure and volume at 0.055. So I'll actually change the volume to cubic meters, but for whatever reason, I'll leave it in atmospheres for the moment. It said it first doubled its volume. And I believe it said at constant pressure. Its pressure is held constant and heated until the volume is doubled. So it would follow this type of path on a PV diagram. And then kind of the same thing here. It is heated at constant volume until its pressure is doubled. So making it about double. Oh, shoot, no, this would be 1. I just want to go to here, double. And so it's going to 2 atmospheres. So ignore that extra space up there. See if any of my whiteout works here. But There we go. Yeah. Okay. And I guess I don't need to do anything quite like that. I just want to know that it doubles. But here's kind of what I'm getting at. Notice it told us how many moles, and it also told us the pressure and volume. So if I call this point A, I also know its temperature. Because if I take the pressure, which I'll write as 101,300, and its volume in cubic meters, 0.055, and I divide it by the number of moles, which is 2.25 and 8.31, a lot like we did in the last problem, we're looking at about 298 for the starting temperature. So room temperature here. Okay. 25, maybe a hair warmer than room temperature. It'd be 25 Celsius. But watch this. If we go PV equals to nRT, and you think about it going from point A to point B, and you are doubling the volume, but keeping the pressure constant, this side doubles, so this side must double. So this 298, if we double it, just becomes a 596. Because you could put in all your pressures and volumes and number of moles and still get also 596. But I think just looking at how it changed and, oh good, I get a chance to say it again, reading the math and the structure of the math, I can just say that one's going to double. Because I'm going to do the same thing again when we go from B to C. In that case, we're holding the volume constant, but we are doubling the pressure. So again, this side is doubling, which means that the temperature has to double. So this 596 is going to double again and become 1192. And so now I have pressures and volumes and temperatures everywhere along this path. Now, I'm not even sure I need all those. I guess I should jump to the question here. The first one doesn't look like I need the temperature because it says, what is the work done on the gas? And I guess I would say it's the area under the curve. And so the work is negative of the area. Of course, I could also look up and say work for constant pressure is minus P delta V. That also works, but that's the area under the curve. And so to get this area, this rectangle, I would take the pressure and the delta V. And notice it should be a negative number because we're talking about the gas expanding. Notice also that the B to C, the work is 0. So when they talk about the two processes, we're really only talking about the part where the gas expands, and there is no expansion, and 0 work is done during the isovolumetric, as I think you know. And so whether you want to use a formula we derived for the isobarometric work, or just look at the graph and say it's the area under the curve, we would get the height of the rectangle, 1 atmosphere, so 101,300. And the volume here, since it doubled, the difference is 0.055. And so we're looking at a negative 5,500, and let me call it 72 joules of work. So the expanding gas did work on the environment, and it only did it in the part from A to B. But there would be the answer, I guess, to A. Now, B is the change in entropy. And the change in entropy means we have to solve this integral. But a Q, maybe I'll put it up here in the corner, for either constant volume or constant pressure is NCV or CP delta T. And so this microscopic amount of work is NC, and either a V or a P, dt over T. And so one of the formulas we worked out was how do you calculate the change in entropy when you have a constant volume or a constant pressure. And then fortunately, the process is a lot the same, because then you just have to integrate dt over t, which is a natural log. So if we go from initial to final, we're going to have the natural log of final over initial. And what's nice about that is in both cases, A to B and then B to C, it's doubling. So this is just going to be an ln of 2 in both cases. In other words, if I go A to B, I would have NCP natural log of 2. Because A to B, I've doubled the temperature. The final temperature is twice as much as the original. And it's constant pressure. Whereas when I go from B to, and I label it C, C, it would be NCV natural log also of 2. So the total entropy, when you add them together, would be an N, and then you would have CP plus ACV over natural log of 2. And for that matter, we need to look at what type of gas we have. What was this, a monoatomic? Yeah, neon. So we have 3 degrees of freedom, so there's CV, and then CP would be one more R on top of that. So 2.5 and 1.5 makes 4 R times natural log of 2. Okay, so to get a number, I'll take the number of moles times 4 times R times the natural log of 2. And it looks like 51.8. And I guess I didn't put in my units here, but they would have worked out here to joules per Kelvin for the entropy change. So we've got the work, and we got the entropy. So we've got A and B. Nice. All right, then on to the last problem. So page 5. Good. I'm glad none of them have taken more than a whole page. Let's see what happens here. Okay, so number 5, again, we also have a monoatomic. We have helium gas this time, but that's really not going to change any of our thought process. But helium gas is taken through this cycle shown here. So we go from A to B to C and back. The scale of the vertical axis is set by PB. Oh, I see. Let me just call it thousands. So this is 7,500 pascals, and it's 3 notches up. So that means the pressure at AC would be 2.5 kilo, which I'll write as 2,500. So, as I said, the sizing of the scale is set by the lines here. So this is 2,500. I guess right here then would be 5,000 if we need it. And this would be 7,500. Okay. And across the bottom here, it looks like we've got a 1, 2, and 3 cubic meters. So some simple straight numbers here. They also tell us, though, at point A, we're at 200. Okay. So I'll put a 200 there. And then what's the efficiency of the cycle? Okay. It sounds like it's going to be a few calculations there. And then what is the maximum efficiency? Now, that's code word for saying what is the Carnot efficiency, which we know to be 1 over the temperature of the cold over the temperature of the hot. which I don't have directly knowledge of those, but remember, I do have pressure, volumes, and temperature. So I could get the number of moles here and then use that to get the temperatures at B and C. Although maybe even easier, I could do what I did in the last problem and do a proportion here, because we go from A to B, which is a straight line. And so that wasn't a process that we had a name for. It wasn't the isobaric, isovolumetric. And so let's, not give it a name other than A to B. But the B to C and the C back to A, this is isovolumetric and this is isobaric. And that's a lot like the problem before it, where here we said we would be doubling the temperature because we doubled the volume. Same logic here. We are tripling the volume and holding the pressure constant. So this goes up by a factor of 3, which means the temperature must go up by a factor of 3. Or in this case, we're cooling down. So, because we're going from C to A. But if we went A to C, we'd have to go up by 3. So if I multiply by 3, this would be 600 is what I'm getting at. So the temperature at C should be 600. Should just be 3 times that of 200. And likewise, the B and C connection here, where the volume's held constant, but the pressure has tripled, the temperature has to triple. So this must be 1800. And so we're going from the high temperature of 18 down to 600. But once I have all those temperatures, maybe I'll just do B first, because the Carnot cycle is based upon the temperatures here. So the most we would expect to get out of here without, violation of conservation of energy is 1 minus the low temperature at 200 and the high temperature at 1800, which I guess reduces to 1/9 or 8/9. That must be 88.88888% repeating, right? 8 divided by 9 repeats, yeah. So this is the most efficiency, which is a big number. That's actually very efficient, but you can then see it's also very hot and very cold, which, again, the efficiency is related on those. So not a big surprise on that one. But A might be a little more work for me to do here. So maybe I should put an A to B, a B to a C, and a C back to, C back to an A. And look at the delta E, the Q, and the W. And go total. Because if I'm looking for the efficiency, I would want the total work divided by the heat going in. I guess I could also do that by 1 minus the heat coming out, the cold environment, and the hot. Now, in both of these, I need the hot. And so maybe we should look at what's happening. And it looks like A to B, thermal energy has to go in because we are increasing its volume and its temperature. So here's where a lot of energy would have to go in. But from B to C, energy would have to come out, and then also C to A, energy would be coming out. And so these two together would be the energy going into the cold environment. And this one by itself would be the energy of the hot one. And so maybe that's how I'll do this problem here. On the other hand, the work wouldn't be too bad, because that would just be the area enclosed by a triangle, and getting the area of a triangle is pretty easy. In fact, let me go that direction. So this right here should be negative of the area. So the area of a triangle is 1/2 base times its height. Let me grab my calculator here. 1/2. The base is 2 cubic meters, and its height is 5,000. Oh, well, those just cancel. I should count to be 5,000. So this should be negative 5,000 joules. And that, of course, makes sense. Hopefully makes total sense, because, you know, we want energy to come out. If we want this to be a successful engine, we want the energy to come out. Now, I think that actually might be the way to go, because I also know on a full cycle, it gets back where it started. So the net amount of thermal energy added in, oh yeah, this is going to be the way to go, because is 5,000. And so one's a positive and one's a negative. You see, what I'm concerned about here is calculating thermal energy during this A to B is one of these steps that we didn't go through. You know, it's not the magical 4, the what is it? Isovolumetric, isobaric, isothermic, and adiabatic. And so we have a system of equations that we could go look up in our notes to get the Q for any of those, but A to B is a path we didn't really work on. And that's, you know, this here, which is the Q hot. And I need that number whether I do this method or this method. So I think the strategy then is going to be use the isovolumetric and isobaric process to get this number, knowing the total brings us back to this number. And that's the key step. Okay, so let's do this. The B to C would be isovolumetric. So it'd be NCV delta T. And so the N, we're not told the N, but I did comment, and maybe we need to do a side calculation. You know, right here at the beginning, they gave us pressure, volume, and temperature. Okay, so we need to find N. So PV over NR is going to give me the number of moles. So let's do the point A here. So 2,500 is the pressure. The volume is 1. Divided by, oh, that was a silly way. Okay. Divided by the temperature, which is 200, and divided by the R, looks like it's 1.5. So I have 1.5 moles. So right here, I'm going to go 1.5 moles. The CV I know from the degrees of freedom, so that's 3/2 R. And the B to C, of course, would be the temperature at C, 600, minus the temperature at B. And so that's a negative 1,200. And so putting these numbers into my calculator, 1.5 times 3 over 2 times 8.31 times a negative 1,200. And so this is, not a surprise, negative 22,437. So in my little chart here, I'm going to put a negative 22,437. And of course, negative means energy is coming out, which again, this is the cooling down process of B to C. We are lowering the pressure. And we can do the same thing for the C to the A process. The Q would be now a constant pressure, but it would be NCP delta T. And 1.5, and then CP would be 5/2 R. And the final temperature would be 200, and the initial is 600, which is negative 400. So again, not a surprise, a negative number. But this would be 1.5 times 5/2 times 8.31 times a negative 400. And so this is going to be a negative 12,465. Let me put that into my chart. Negative 12,465. Okay, so these two together would represent the cold one. And this one is the one I'm really looking for. I think I'll use this formula because I already know the work, 5,000. Now I just got to figure out the heat, but this plus this plus this got to give me a positive 5,000. So if I put these two negatives together, these two together are 34,000. If I imagine that equation, these three have to equal that. I move it to the other side, it would become positive. So let me just multiply it by a negative 1. And then I would add it to the 5,000. And so this would be 39,909 and a plus. Okay, so finally getting the efficiency of this real engine. I've got the work being done in absolute values is 5,000 joules. And the heat being added to it is the 39,902 joules. So 3,000 divided by the last answer is about 12.5%. 12.5%. Yay! And I think that's it. We done? Yeah. And the A and B. Okay. So hopefully you learned a lot from any mistakes you might have made. Thermodynamics, always a tough topic, so I hope you did well. Like I hope you got some idea of what your grade is. Take care, everybody.